15.5 is about surface integrals. Applications of these: fluid and heat flow, E&M, mass, center of gravity. We'll see some of these later on, but it's actually pretty similar to what we did with in 14.8 when we did the mass of the little lamina. Okay. The idea here is that we're going to integrate over a smooth parametric surface so instead of having a little lamina in the xy plane, now what we're going to have is maybe a thin, we can think of it as a thin curved plate. So a thin curved plate. So now instead of having surface in 2 dimensions, we're going to integrate potentially a surface that's more easily described in 3. Okay, now how do we do that? So first let's start with an interpretation. Which is that we could approximate the mass, kind of like what we did earlier, by taking the sum of, let me redraw this, each little piece. So if I take any location along this thin curved plate, we can assign corresponding coordinates x sub k star, y sub k star, the usual, z sub k star. We'll call sigma sub k the kth patch. And now, when we try to find the mass, what we're going to do is take the density function, which we're going to call f. So just to make that clear, we'll label this density function. Evaluate it at that particular point, x sub k star, y sub k star, z sub k star. And now, in 14.8 we had an area. This is where the dA came from. Instead of calling this delta A sub k, I'm going to call this delta capital S sub k. And this again will denote the surface area of each patch. And eventually, as we take the limit, so taking the limit as n approaches infinity, so now we're going to add up all the little masses of all the little patches. Eventually we're going to get the mass of the entire parametric surface, and this is where we get our definition from. Okay, so the definition looks something like this. If sigma, and this is little sigma, is a smooth parametric surface, then what we call the surface integral of f of x, y, z over that surface looks something like this. It's a double integral. We have this little symbol here, which really could be any symbol. I mean, you'll know it's a surface integral depending on the context, but typically you'll see this. You have your function on the inside, f of x, y, z, which right now we're interpreting as a density function. And then you'll see d capital S, not to be confused with d little s, which represents an arc length parameter. Now, if you're even thinking that this is an arc length parameter, you'll know that it shouldn't be because this is a double integral. Okay, so this needs to represent not a length but an area of some sort. Okay. Now, here, so continuing our interpretations, one of them we already discussed. This is mass. And if we just did surface integral without a density function ds, what would this represent? Surface area. If the density function's constant, it's just like what we did earlier, right? Instead of having the length of a thin little wire, now this is going to represent the area of that thin little plate. Okay? All right. So obviously the question is going to be, how do we evaluate these? Okay, right now, this is pretty much what you need to know they represent. In the next section, in 15.6, we'll have a tie back into what we've been working on with vector fields, and we'll see where these come in. Yes, Eddie?
Is this any different than the other integration we used to find surface area?
Is this any different? A little bit. And I think you'll see that it's actually very similar, but there are some minor differences. So you'll see some of the stuff that we did when we did surface area. Okay. So how do we find these? Well, there's going to be really two ways to do this. Okay, if we are in a parametric setting, then we're going to say that the surface integral of f of x, y, z ds is going to be a double integral. We're going to plug in our parameterization for the surface, much like we plugged in the parameterization of a path into our function. We're going to change this to now over a region R. And now the part of the surface area that we need to be careful with is here. I'm running out of space, so I'm just going to write this here. The surface area formula, which if you recall from 14.4, was, I believe, magnitude of cross product between partial R, partial U, partial R, partial V. What's that?
What was that? Was that the...
That's the surface. What's the what?
Was that the Jacobian? Or was that...
No, this is the actual surface area of the surface.
Oh.
The Jacobian was determinant. I mean, you can kind of think of it as a scaling factor. If we're doing a surface integral that's set up as this integral here with respect to the surface area, when you change it to rectangular coordinates or find a parameterization for it, you can think of this kind of like the Jacobian, but I mean, what it really represents is the surface area of the surface. Okay. So I'll actually do an example with this one, and then we'll talk about rectangular, finish with an example in that mode, and then we're done. It's a pretty straightforward section. Alright, so let's say we wanted to evaluate the surface integral of x squared ds over the sphere x squared plus y squared plus z squared equals 1. Okay, so far we only know how to evaluate this integral if it's parameterized. Okay, so do we have a parameterization for a sphere that we could use?
Yeah.
What is it?
Are you talking about like changing the spherical?
That's the right idea, yeah.
Rho equals 1. Would that be what you're doing?
Okay, but we'll backtrack a little bit. We can't change the sphere because it's not a triple integral,
Okay.
but we do want to think spherical coordinates.
Uh-huh.
Do we know what x is in spherical, y is in spherical, z? So x is rho sine phi cosine theta. Now, here's what Eddie says actually comes into play. This needs to be in terms of two variables. The link that we have between rectangular and a parameterization for it is in three variables, but we know what rho is. We know that rho is 1, right? We know that rho is 1, so then we do actually have a parameterization for the surface in terms of just two variables. So let me rewrite this. We're going to say x is just sine phi cosine theta. Y would be rho, which is 1, times sine, sine phi sine theta. And then z was rho cosine phi, so 1 times cosine phi. So this represents not r of uv, but in this case, r of, let's call it phi theta. Okay, so phi and theta are taking the places of u and v here. Okay, so now to evaluate the integral, here's the roadmap. X is going to get replaced with the parameterization for x. And then the ds, we have to figure out basically the surface area, okay, using these variables. So let's find partial r, partial phi, cross that with partial r, partial theta. Okay, so if I look at, and again, this represents the components of r right here. If I look at x and take the derivative of that with respect to phi, what do I get? Here's x. With respect to phi, it would just be good. And then we just go each component with respect to phi, so then y would become, yep. And now z with respect to phi, yes. And now we find partial r, partial theta. So take each component, differentiate with respect to theta. Now we get yep. Yes. Middle one. Yep. All right. So let's figure out this cross product. First term, we get 0 minus a negative. It becomes sine squared phi cosine theta. The middle component, we get 0 minus a positive, but we do the opposite of that. So it's going to stay positive. And it's sine squared phi sine theta. And now the last component, we're going to take this product minus that one. So we get cosine phi, sine phi, cosine squared theta, plus cosine phi, sine phi, sine squared theta. Was there a question I can clarify, or did we?
Did you get rid of the cosine squared sine squared since t equals 1?
Right here?
Yeah.
Absolutely. So the final version that we're going to use is sine squared phi, cosine theta, sine squared phi, sine theta. And yeah, if you factor out the common factor, you get cosine squared plus sine squared. So this will just become cosine phi, sine phi. Okay, so that's the cross product. So I mean, it does take a little bit of work, but hopefully doing all this will make the integral not horrible. So now we want to find the magnitude of that, because that's what we're going to stick in the integral. So the magnitude would be the square root of the square of, or the sum of the squares of all these components. So that's sine of the fourth phi, cosine squared theta, plus sine of the fourth phi, sine squared theta, plus cosine squared phi, sine squared phi, which we can clean up. From these first two terms, I can factor out a sine of the 4, leaving behind cosine squared plus sine squared theta, which is 1. This becomes sine of the 4 phi plus cosine squared phi sine squared phi, which I could still factor a little more. We can take out sine squared phi, leaving behind sine squared phi plus cosine squared phi. So then this is just going to be sine phi. All right. So let's set this up. So all that legwork is done. Now we can actually start evaluating the integral. The surface integral of x squared ds is going to become, let's see, x squared. We plug in the parameterization we had for x, which was sine phi cosine theta. So that'll be sine squared phi cosine squared theta. And now we need the magnitude of the cross product, which was sine phi. And we changed our parameterization to thetas, or phis and thetas, so we're going to do d phi, d theta. All right, so now what are the bounds for phi and theta? We didn't write them down earlier, but we can go back and do that. This represented a sphere, right? So theta, let's do phi. Phi has to be between, good. And then theta is, good. So we plug in those bounds. 0 to pi, 0 to 2 pi, and now we evaluate. Sine squared sine phi becomes sine cubed. How do we work with sine cubed?
Pull out a sine and use the trig ident.
Pull out a sine And then the trig identity for sine squared.
Is cosine squared.
Good. So what we're taking is sine cubed phi. We're splitting it up. This becomes sine phi minus sine phi cosine squared phi. So then that's what we're going to, because we're going with respect to phi first, so that's what this, we need to think of sine cubed as this function over here, so that when I integrate, the sine phi part becomes minus cosine phi.
Wait, isn't it supposed to be 1/2?
1/2.
No, it's a different formula.
Oh,
It's
it's a
just
different
the
formula?
1 minus cosine squared equals sine squared.
Oh.
Oh yeah, we're not using the half angle formula. We're using cosine squared plus sine squared as well. Okay, so back to sine cubed. The first half of it becomes minus cosine phi. The second half of it, you can think of cosine phi as your u, because then du is right here, minus sine phi. So this becomes plus 1/3 cosine cubed phi. And we still have cosine squared theta. And this is from phi equaling 0 to pi d theta. So now if we plug in the bounds, let's see. This becomes a 1 minus 1/3 times cosine squared theta. Then we're going to subtract. Now we plug in 0. So that becomes negative 1 plus 1/3 cosine squared theta d theta. That's just 4/3, right?
Yeah.
Let me pull that out. So 4/3, and then cosine squared theta. And this is the formula, or similar to what you were thinking of, Eddie, I think. Cosine squared, we're going to rewrite as
1/2 is 1/2 cosine 2 theta.
good. So this becomes 4/3 times the quantity 1/2 theta plus 1/4 sine 2 theta, evaluated from 0 to 2 pi. 0 and 2 pi. Let's see, that's just going to give us 4/3. Canceling out the sine term, but half times 2 pi is pi. So 4/3 times pi. Okay, so as you can see, sometimes the process is not short, but works out sort of nicely. Okay. Any questions on how we did that? All right, well, I guess we don't need to derive this. Do you guys remember the surface area formula that we did with rectangular? Like if we wanted to find the surface area using a double integral, what did we integrate?
1/2.
That's what I'm looking for. So both are correct, depending on
What?
what you're talking about. If you're finding the area of a region, that's double integral of 1dA. If you're finding surface area, we wanted to put in the integrand the square root of 1 plus partial x squared plus partial y squared. Does that sound familiar?
No.
Yes.
Okay. If it doesn't sound familiar, look back at the notes from 14. At some point we did it.
It's 14.
Yeah. So instead of double integral, let's say instead of having a parameterization, if we are all rectangular, so if rectangular, then the surface area of f of x, y, whoops, that should be an f of x, y, z. That's just a large comma. I'm sorry, that looks really bad. That's better. The surface integral of f of x, y, z ds will become a double integral over region R. We still have the density function, f of x, y, z. And now, instead of using the parametric surface formula for surface area, we'll use the square root of partial z partial x squared plus partial z partial y squared plus 1 dA. Okay, so it should be. I remember you guys complaining a lot about 14.4. That could have something to do with some of you not remembering this.
I vaguely remember, yeah. And then you said it was like 1 is not 217.
Because that's in 14.4 is when we did surface area. We also introduced the R of UV stuff and how to parameterize the surface. We also revolved stuff around axes, which we didn't really do again, except for in class and in the homework, I think. Does that sound familiar? Okay. Anyway, let's do one last example, and then we're done. So let's say we have surface integral of y squared plus 2yz ds. And we'll say that the surface sigma is the first octant portion of 2x plus y plus 2z equals 6. Okay. So, we know what y is going to be. I guess we should maybe write it down, but actually, no. Sorry, let me backtrack. We know that y is good because we want x's and y's in the formula here. What we don't want is z. That's what I meant to say. But this formula here, the equation for the plane, tells us that z is what?
1/2 6 minus 2x minus y.
What was it? Sorry.
1/2 times 6 minus 2x minus y.
1/2 times
6 minus 2x minus 1.
You can simplify that.
good enough. So then, once we have z alone, now we know that that's what we're going to replace in here. And now we have a formula for z that we can take partial x from and partial y from to figure out this square root in the integrand. Okay, so partial x is going to be -1, partial y, -1/2. So then the square root of partial x squared plus partial y squared plus 1 is just going to be 1 plus 1/4 plus 1, which is, what was that, 3/2? 8/4, 9. Okay, so 3/2. So now let's rewrite the integral. So we're going to have y squared plus 2y, but now z is going to be 1/2 times 6 minus 2x minus y times 3/2 dA. So I'm just replacing z with what z is equal to. ds becomes the square root of all that stuff, which we figured out was 3/2, and then we still have the dA here. All right, so let's clean this up and set up our bounds. The 2y and the 1/2 just give you y, so that's 6y minus 2xy minus y squared, thank you, times 3/2. Actually, let me just,
I cancel out the other y squared.
yep. So then we just have 6y minus 2xy times 3/2. And let's go dy dx. And let's plug in the bounds now. So if you forgot, first octant portion of this, that really just meant that we had a plane cutting through. Z-intercept was 3, x-intercept was 3, y-intercept was 6. Okay, so then y would be from what to what?
0 to x minus 2x. And 6 minus 2x.
0 to 6 minus 2x. So we're going from right here to this line. Lower bound for y, upper bound for y. This is just y equals 6 minus 2x over here. And then x would be from 0 to 3. Okay? You guys just want to trust me here? At this point, I think you guys know how to evaluate these. So, I think the key is setting them up. So in this section, you only have to do one thing, and there's two ways to do it. Find a surface integral. One way would be to do it in terms of u and v, or any two other variables besides x and y. Or if we stay with x and y, we have a way to do that as well. All right? Do you guys have any questions?